What is the universe actually made of? I mean, really made of? It's maybe the oldest question we have.
Right, we look up, we see stars, galaxies.
So what if most of it is invisible? Something called dark matter and dark energy.
Exactly. And these aren't just, small footnotes. They're the main story.
Okay, let's unpack this.
Well, think about the numbers. When we measure the universe's total energy and matter budget, say with WMAP or the Planck satellite.
Those are the missions that map the afterglow of the Big Bang, right?
Precisely. Their data tells us something pretty staggering. Dark energy makes up something like 68 to 71%.
Wow.
Dark matter, maybe 24 to 27%. And the stuff we know, atoms, stars, us, and like 5%, maybe less.
So 95% of the universe is dark. Stuff we don't understand.
That's the scale of the mystery we're dealing with. It dominates everything.
Okay. So for this deep dive, we've got a couple of really interesting sources to guide us. First, there's a research chapter by Ekram Odner.
Ah, yes. The one proposing that maybe the interactions between all these components matter, dark energy, maybe that's the key. A pretty radical idea.
And second,
a report from a Department of Energy workshop on dark matter. This one's all about the nitty-gritty. How are we actually trying to find this stuff? The experiments.
Got it. Theory and experiment, tackling the same unknowns.
Exactly. So our mission for you today is to give you a real insider's look at how science is grappling with these huge questions. You'll get a handle on some cutting-edge theories and the amazing technology being built to test them.
Frontiers of physics, basically.
Pretty much.
Okay, so let's set the scene a bit. This quest to understand the universe, it connects the incredibly small, like particle physics.
The microcosmos, quarks, leptons, bosons.
The standard model of the incredibly large cosmology.
Yeah.
The Big Bang, galaxies, the whole universe.
The macrocosmos. And these two fields, they're deeply intertwined. You can't really understand one without the other.
And we've had huge successes, right? The standard model is amazing at describing particles.
Phenomenally successful. It classifies the fundamental building blocks, their forces. I mean, finding the Higgs boson was a massive confirmation.
And the Big Bang theory. It explains so much about the universe's history.
Absolutely. Hubble's discovery of expansion, the cosmic microwave background radiation, the amounts of hydrogen and helium. It all fits the Big Bang picture beautifully.
But there's always a but in science, isn't there?
Usually. Despite all that success, both models have, well, let's call them blind spots, unanswered questions, missing pieces.
Like what? What are the big head scratchers for the standard model?
Oh, quite a few. Why do particles have the masses they do? This huge range, the mass hierarchy. Where are the magnetic monopoles theory predicts? Why is there so much more matter than antimatter, the baryon asymmetry, the strong CP problem? It's a list.
And for the Big Bang model?
Similar story. What exactly was the initial singularity? What drove that incredibly rapid expansion phase called inflation right at the beginning? And maybe the biggest one right now. Why is the expansion speeding up now? That late time acceleration. Plus, again, the baryon asymmetry, how galaxies formed.
So enter dark matter and dark energy. They were kind of proposed to patch some of these holes.
Initially, yes. Dark matter seemed to explain why galaxies rotate too fast for the visible matter they contain.
Right. Something unseen must be providing extra gravity.
Exactly. And dark energy was invoked to explain that accelerating expansion we just mentioned. Something must be pushing the universe apart.
But even then, they're still just placeholders, almost.
Yeah.
Within the standard Big Bang framework, we don't know what they are.
Precisely. Their fundamental nature, their role, it's not explained. And the kicker, we haven't directly detected either one. All the evidence is indirect gravitational.
Okay, so that leads us back to that first source.
Yeah.
If the standard models aren't enough, maybe we need a new way of thinking, like these interactions.
Right. This is where Adiner's work and the chaotic universe theory, or CUT, comes in, proposed back in 2018.
Chaotic universe theory. Sounds dramatic.
It kind of is. The core idea is nonlinear interactions. Matter, dark energy aren't just coexisting, they're dynamically interacting, maybe even transforming into one another.
Whoa. So not static components, but players in a cosmic dance.
Exactly. And this leads to a chaotic dynamic. It's proposed as a chaotic cyclic model, so the universe goes through cycles of expansion and contraction, but driven by these interactions.
How's that different from other cyclic models?
The key is chaotic. The cycles aren't perfect repeats, and it
Mhm.
potentially explains things like cosmic inflation and the different eras, radiation-dominated, matter-dominated, dark energy-dominated, as periods where one component is just, well, dominant due to these ongoing transformations.
Okay, that's a really different picture. What problems does it solve?
Well, according to the theory, it avoids the dramatic cosmic fates, like the Big Rip, Big Crunch, or Big Freeze.
Where the universe either tears apart, collapses, or fades into nothingness.
Right. In CUT, our current universe is just an intermediate phase. The beginning of our universe was the end of a previous one. Our end will be the start of the next one.
So no absolute beginning or end, no singularity.
That's the claim. It gets rid of that problematic infinite point. And the cycles being chaotic fits with ideas from chaotic inflation theory. Tiny changes in initial conditions lead to very different outcomes in each cycle.
And does it connect to things we can, actually observe?
Potentially. It suggests galaxy formation might arise from local attractors within this chaotic system,
Hmm.
like little whirlpools where matter clumps together.
Yeah.
And it might provide a mathematical basis for the fractal patterns we seem to see in the large-scale structure of the universe. Chaos theory often generates fractal.
Fractals in the cosmos. That's wild.
It also touches on deeper, almost philosophical ideas, doesn't it? About existence, creation, continuity.
Yeah.
If the universe is this eternal, chaotic cycle.
It definitely makes you think.
Yeah.
But you said it's still a developing theory.
Oh, absolutely. It's not fully fleshed out. It needs more theoretical work, and critically, it needs experimental or observational evidence to really back it up. It's a compelling idea, but not yet proven.
Okay. Let's shift gears a bit to that accelerating expansion. You said it was discovered using supernovae.
Yes, type A as supernovae. They're like standard candles. We know how bright they should be, so we can measure their distance accurately by how dim they appear.
And in 1997, astronomers found they were dimmer, further away than expected.
Exactly, which meant the expansion of the universe hadn't been slowing down as everyone thought due to gravity. It had actually started speeding up at some point. A huge shock.
A shift from being matter-dominated, where gravity slows things down, to dark energy-dominated,
Right.
where something pushes things apart.
Precisely. The old Friedman equations describe how the scale factor, A, the size of the universe, grows over time, T. For radiation, it's roughly like T to the power of 12. For matter, T to the 23, slower growth. But dark energy means something more like exponential growth.
So the big questions became, why did it switch? And when?
And this is where CUT, focusing on those dark matter-dark energy interactions, offers a potential answer. The researchers derived a mathematical formula for the scale factor, a kind of hybrid.
Combining the matter-dominated and dark energy-dominated parts.
Exactly. It looks like A0 to D xt0. The x to the alpha part represents the matter era, and the exponential part represents the dark energy push.
And did they find values that matched observations?
They did. Remarkably, they derived that alpha value to be exactly 23, just like the standard Friedman model for a matter-dominated universe.
Okay, that's consistent.
And the parameter h, which relates to the expansion rate or the Hubble parameter, came out in a range that perfectly matches the measured values from WMAP, Planck, Hubble Space Telescope data around 0.7 or 70 kilometers MPC in cosmologist units.
So the model fits the data we have now. But what about the when? When did the transition happen?
This is maybe the coolest part. The model calculates the transition point. The moment when dark energy starts to dominate over matter occurred about 9.8 billion years after the beginning.
9.8 billion years. How does that compare to other estimates?
It's right in the ballpark. Other methods estimated around 9.4 to 10.2 billion years. So excellent agreement.
And why is that timing significant? You mentioned the cosmic coincidence.
Right. The cosmic coincidence problem is basically asking, why are we living at this seemingly special time when the density of matter and dark energy are roughly equal? If dark energy always existed, why did it only take over relatively recently in cosmic history?
Ah, I see. It seems unlikely we just happen to be around at the exact moment of this cosmic power shift.
Exactly. But this model, derived from CUT, predicts this timing naturally. The transition happens around 9.8 billion years because that's when the dynamics of the interaction dictate the densities become equal. It solves the coincidence.
That is neat.
Hmm.
And the paper connects this timing to life.
It makes an intriguing suggestion, that 9.8 billion year mark. Well, how old is the Earth? About 4.5 billion years. The universe is about 13.8 billion years old.
So life arose on Earth when the universe was roughly 9–10 billion years old.
Something like that. The earliest signs of life are maybe 3.7, 3.8 billion years ago, meaning the universe was around 10 billion years old. The paper points out this timing is a very close match with that calculated cosmic coincidence point.
Kind of like the universe became hospitable, or the conditions were right. Around the same time, dark energy started taking over.
It's consistent with something called the anthropic principle, the idea that the universe's properties must be such that they allow life like us to observe it. Maybe complex life could only really emerge around this transition point.
Wow, that adds a whole other layer. But again, this relies on the COT model being correct, right?
Absolutely. These are successful predictions from the theory, which lends it indirect support. But it's not the same as directly finding dark matter or dark energy.
Which brings us perfectly to the second source, the Department of Energy report on the hunt for dark matter. How do we actually find this stuff?
Right. We need direct detection. This stuff makes up over 80% of the universe's matter, yet it's completely invisible to our telescopes. Finding it would be revolutionary, likely pointing to physics beyond our current standard model.
So the DOE report outlines key directions.
Yes, 3 priority research directions, or PRDs. These are focused specifically on looking for dark matter particles lighter than a proton. Most big experiments so far, the Generation 2 or G2 experiments, have focused on heavier candidates, particularly WIMPs.
WIMPs, weakly interacting massive particles.
That's them. These new PRDs are smaller projects, maybe 5M, $50 bellers, designed to be agile and leverage existing DOE facilities to search this lower mass range.
Okay, let's break them down. PRD1.
PRD1 is creating dark matter in accelerators. The idea is if dark matter was created in the hot, dense, early universe, maybe we can recreate those conditions by smashing particles together at high energies.
Make our own dark matter.
Essentially, yes. One thrust is to massively boost sensitivity like 10 to 1,000 times to search for thermal dark matter candidates between the mass of an electron and a proton.
How do they look for it if it's invisible?
Couple of ways. Missing momentum experiments, you smash things together, measure everything that comes out, and if the momentum doesn't balance, you infer something invisible carried some away.
Ah, clever. Like seeing footprints, but not the creature.
Kind of. Another way is beam dump scattering. You fire a beam into a target, stopping it. If dark matter is produced, it might pass through the target and scatter off detectors placed downstream. Places like CBAF at Jefferson Lab or Fermilab are key here.
And there's a second thrust.
Thrust 2 involves looking for unstable dark sector particles using spectrometers. The big goal here is if you make it, you can study it. Determine its mass, its spin, how it interacts. That would be huge.
Okay, making it. What's PRD2?
PRD2 is detecting galactic dark matter particles. This is about catching the dark matter that's already here, flowing through us right now from the Milky Way's halo.
The cosmic phantom breeze idea.
Exactly. These experiments are incredibly sensitive, usually deep underground, to shield from other interfering particles, like cosmic rays.
What mass range are they looking at here?
From the proton mass all the way down, like 12 orders of magnitude lighter, it's a vast range. They look for tiny signals, a vibration, phonon, a released electron charge, or a flash of light when a dark matter particle hopefully bumps into an atom in the detector.
What kind of detectors?
All sorts. Thrust 1 focuses on interactions with the atomic nucleus, using things like big vats of superpure liquid xenon or argon, or crystals of germanium or silicon cooled way down, even superfluid helium.
And thrust 2.
Thrust 2 looks for interactions with the electrons in the atoms, which is better for probing lighter dark matter. They use similar materials but also cutting-edge stuff like superconductors or even single layers of atoms like graphene.
If one of these experiments gets a hit,
Right.
that's direct proof.
That would be the smoking gun. Direct evidence that this particle exists and makes up the dark matter in our galaxy. Game-changing.
Okay, one more. PRD3.
PRD3 is detecting dark matter waves. This targets the ultralight end of the mass spectrum, maybe from 10 to the minus 22 electron volts up to 1 electron volt.
So light, it behaves like a wave, not a particle.
Exactly. Think of it like a pervasive, oscillating, field-filling space. A really well-motivated candidate in this range is the QCD axion.
The axion. I've heard of that. Doesn't it solve some other particle physics problems too?
It does. It elegantly solves the strong CP problem in the standard model, and it could also relate to the hierarchy problem. So finding it would solve multiple puzzles at once.
How do you detect a wave like that?
Thrust 1 uses technologies ready now, like extremely sensitive resonant microwave cavities. Basically, if the axion wave has the right frequency, it can convert into a detectable microwave photon inside a strong magnetic field. They're aiming for a frequency range covering a good chunk of the likely axion territory.
And thrust 2. looking further.
Thrust 2 is about developing future technologies to cover the rest of that huge 20 order of magnitude mass range. Things like atomic interferometers, supersensitive magnetometers, torsion pendulums for the very lowest masses, and advanced quantum sensors for higher frequencies.
What's cool here is that finding something this light wouldn't just tell us about dark matter.
Right. It could give us clues about physics at incredibly high energy scales like grand unification or even quantum gravity, and tell us about the very early universe, maybe even inflation itself.
So 3 very different approaches. Make it, catch it passing by, or detect its wave-like effects.
Exactly. And they're complementary. They cover different mass ranges, different types of interactions. If there's a discovery, we'll likely need signals from multiple types of experiments to really understand what we found. It's a broad, coordinated attack on the problem.
And sounds like it relies on a lot of collaboration.
Hugely. You have the theorists proposing models and targets, guiding the experimentalists. You need advances in basic detector technology, drawing on fields like quantum information science.
UIS.
There's synergy with neutrino experiments, which often use similar detector technologies like liquid argon, and it all leverages decades of investment and expertise at DOE labs and accelerators, cryogenics, magnets. It's a massive ecosystem.
It really highlights how science builds on itself.
It really does. And, even if these searches don't find anything in the expected ranges,
It's still useful information.
immensely useful. Ruling out possibilities is crucial. It tells us where not to look, forces us to rethink our theories, maybe pushes us toward even more exotic ideas about what dark matter could be, or if our understanding of gravity itself needs modification. A null result can be just as profound in its own way.
So what a journey we've covered. From these fundamental questions about what the universe is made of,
Yeah, the 95% mystery.
through some really out there but compelling ideas like the chaotic universe theory, suggesting maybe the components transform into each other in endless cycles,
A potential explanation for the cosmic coincidence and maybe even life's timing.
all the way to the incredible experiments being built and planned, trying to make dark matter, catch it, feel its waves, across just a staggering range of possibilities.
It really underscores that figuring out dark matter is one of the most important goals in science today. It connects the quantum realm to the cosmic scale. It's fundamental.
So maybe something for you, the listener, to think about. How does exploring this dark side of the universe change things? It's not just about cosmology charts.
Right, it pushes technology to its limits.
And it even bumps up against those deep philosophical questions about existence, cycles, maybe even our own place in it all. If we do find dark matter, or confirm a theory like CUT, how might that fundamentally change your perception of reality? What if the universe isn't just expanding, but transforming? Worth pondering.